Hi, everyone. Welcome to today's webinar. We're an automated mapping of clinical entities from natural language text to medical terminologies. I'm Julia Moeller, and I'm joined here today by Andres Fernandez, machine learning engineer and data scientist at John Snow Labs. Before we get started, just wanted to cover a few housekeeping items. So we do welcome your questions today. You are in listen-only mode, so if you have any questions, please be sure to type them into the GoToWebinar control panel on the side of your screen, and we will be answering any questions at the end of the webinar. If you have any technical difficulties, please shoot me an email and I'll try to help you out. My email's there on the screen. And finally, we will be sending out the recording for today's webinar, so you should receive that within the next couple of days. And at this time, I'd like to turn it over to you, Andres.
All right, Julia. Thank you very much for the introduction, and thanks to all the attendees for sharing their time with us and kindly joining our today's webinar. Well, as Julia kindly mentioned, I'm Andres Fernandez. I'm a machine learning engineer and data scientist at John Snow Labs, and today we're going to be covering a bit of mapping clinical entities parts from free-form text into their standardized form in different medical ontologies. So at this presentation, we're going to go, through the actual problem definition. It's kind of its name, its scientific name. Why is this relevant in the healthcare context? Why, solving this problem is relevant at all? And we will find next some technical solutions and discuss a little bit of the technical aspects of this mapping. And finally, we will show you guys how do we at John Snow Labs solve this problem, and what kind of tools do we have ready for you to use and apply them into your own problems, your own situations. At the end, we're going to see a couple of notebooks as a demo and kind of as the results that you will be, getting right out of the box when you start using our library. Okay, so let's start and get the problem definition. So at the heart of mapping different type of entities to their curated or to their normalized versions is the problem of entity resolution. So what is this? What does this mean? What does entity resolution mean? And how can we officially define this problem? We could use a few words and say that entity resolution is the problem of matching different variations of a single concept onto its normalized version, being able to map different ways, for example, of writing the same thing in plain words, right? We can find different definitions, for example, in Science Direct, a little bit more complex, which is probabilistically identifying a real thing based upon ambiguous clues, or a definition in Wikipedia where you can see that is connecting disparate data sources and finding non-obvious relationships, right? Or for example, in the IBM cognitive services, they kind of define it as standardize and optimize records and detect relationships with existing entities. So this is pretty much how everyone how everyone defines the problem itself. But in the medical domain, what does this mean? How can we better put it in pictures or in more or simpler words? For example, we know over clinical notes and free-form text, we get different ways of writing a standard concept like chronic lymphocytic leukemia. We can find it written down like CLL, SLL, CL leukemia, and hundreds of different forms. How do we map those different variations to the original, the green one, chronic lymphocytic leukemia? other example could be, for example, nervous system lymphoma or nervous cyst dot lymphoma or PCNSL or lymphoma CNS and so on. We have many different variations to identify the primary central nervous system lymphoma, for example. Or another situation, we have renal failure or renal disease or CKD or even chronic KDs dot and so on, right? We have different ways of writing this down, and generally simple keyword matching will not do enough to match these versions or variations to the normalized concept. In the general way, we can basically say that is the entity resolution problem is matching a set of multiple variations onto their normalized or curated versions, right? Okay, how do we generally address this problem? Well, it can be subdivided into 5 kind of very consistent stages. These are the pre-processing, right, of the text. We're talking about text. We'll be talking about text most of the talk, right? Pre-processing this text, mainly cleaning the input, cleaning special characters, cleaning typos, spell checking, tokenizing the whole structure. Although first, divide the structure in sentences, then tokenize them, then kind of clean everything, remove stop words, remove, as I mentioned, typos or change slang into the correct way of saying things, right? That's the pre-processing task, a very kind of cheap task in general terms. Then we have the indexing stage. In the indexing stage, we kind of try to form different ways of structures, if I may say, structures to store whatever curated or normalized versions, data sets that we have. We generally call them knowledge bases, and try to structure them in a way that it will be easier to search later. Then we have the stage of comparison, right? We are comparing everything that we have as an input into and try to match these inputs to the knowledge base that we have previously indexed, right? This stage is generally the most expensive one in terms of computing. Then we have the classification task, right? We made all the comparisons with all the entities in the knowledge base, probably all or a subset of them, and then we want to assign a class based on the most similar entities that we found for it. And at the end, if possible, there's an evaluation stage in which we if we have the correct answers for the classification task, we will be then able to perform some kind of evaluation on top of it. Okay, as I mentioned, pre-processing is kind of cheap in computational terms. Indexing, classification, and evaluation are lying there kind of in the middle in terms of computation, and then the most expensive one would be the comparison stage. But wait, we have good news, and these really good news are that we have we have a full toolkit, a full tool set in Spark NLP to deal with all of these 5 stages, at least for the entity resolution part in the Spark NLP Enterprise version. So, okay, we have the concept defined, we have the problem defined, sorry. Why is this useful in the healthcare environment, in a healthcare institution, for example, in a healthcare domain? We have agreed that entity resolution is at the bottom of mapping these entities, mapping these texts to normalized versions. And these entities can be different things. They can be person, diseases, drugs, vendors, partners. And as you may see, all of these entities are present in the day-to-day management of a healthcare institution, of all the healthcare processes. And not to say they're present, not only can we say they are present, but they're at the heart of every healthcare process. So entity resolution will help us, and will actually help us a lot in having accurate distributions
in our data sets over these previous entities. And this will help us in basically generating correct customer segmentations for marketing purposes or for business development purposes, correct disease distributions for either preparedness or for actual reports to government institutions, or even to kind of handle our own resources in terms of medical devices and so on. We can have more accurate drugs distribution in order to help our pharmacy, if we have one, in order to help our procurement and supply chain with correct the duplicated merged distributions. And the same thing for medical devices. We may have exceeding inventory of some kind of devices that are needed to treat different diseases that we do not have, and we found out that we are not having those by performing accurate disease distributions. And when I say accurate, it's code-based, when you can actually find distribution across ontologies like the ones we're going to see today. I don't know, for example, SNOMED, ICD-10, so on. Or if this is not enough, maybe you can, go towards IT domain and start asking yourself, do we have a correct data management system? Entity resolution is at the core of a correct data management system, at least when it has to do with building mastered data sets. And this concept, master data sets, is something that you are really, or must be really familiar with. And if this is not enough, then we have HIPAA. HIPAA actually asks for deduplication of patients in order to keep their clinical histories movable from one place to the other. You cannot have a high number of different clinical histories for the same person disseminated all across your information systems. You need to deduplicate them and merge them and have a single one. So even if these business reasons that we mentioned before do not fit your needs, then you're forced to do so by regulation. Okay. Having said that, well, we now know that it's really useful for healthcare. What are the solutions to these kind of problems? What we must say beforehand, and we actually deep dive, is that most of the entity resolution techniques are based on something called KNN. KNN is an algorithm that it's their letters, or this acronym stands for K as in quantity, nearest neighbors, I mean, as in K, as is in a number denoting quantity, and then nearest neighbors. So that's what it means. Let's find the K. Let's say K takes integer numbers. Let's say 5. Let's find the 5 nearest neighbors for a given entity. And what does nearest neighbors mean? Well, having a set of entities, we kind of want to know which ones are the closest to a given entity. So if we want the one closest entity to the yellow one, in this case we call the query entity, well, we get the green one there. If we want to get the 2 closest, we get the green and the blue one. If we want to get the 3 closest, we get all of those green, blue, and red ones. And this is basically closest definition in terms of some kind of distance. So in this case, as you may see, I didn't draw the axes there, but we're dealing with a 2-dimensional space, and we're just calculating Euclidean distances against between the points. So at the bottom of KNN, we have an entity denoted or described by a vector. In this case, a 2-dimensional vector. In the general case, it's an n-dimensional vector, and then some distances, right, that allow us to calculate distances. So in text, and we're talking about text now, we have 2 problems there. How do we vectorize text? So we usually use techniques like bag of words, TF-IDF, and embeddings. Basically, just to go over them real quick, bag of words is basically a vector, for example, a sentence vectorized in terms of a bag of words technique is mainly when you have a vocabulary and you assign a number to each word in the vocabulary or in the dictionary. A bag of words will basically say, okay, in this document, you have used words 5, 8, 10, and 30 and 32. So that means a bag of words. So you have a vectors of ones in those indexes and zeros in the rest. That's bag of words. TF-IDF is similar to bag of words, but it weights those ones in a way that you get kind of the importance of the word implicit in the number for that you use to substitute the one. And then we have embeddings, that it's a lot more complex way of vectorizing inputs, but is kind of the one achieving best results, at least in the scaling aspect. And then we have distances. How do we calculate distances? Okay, we're halfway through, because now we have vectorized our text, and we will be able to calculate different ways, different sets of distance algorithms. So we have character-based distances. Actually, for these ones, we do not to vectorize text, of course, but these are very inefficient, and they take very long to calculate. So at large scale, we don't usually these ones. And then we have the token, the token vectors based ones, which are Jacquard, Sorensen Dice, and TF-IDF. Mainly Jacquard saying, okay, you have this percentage of tokens in common between these two sentences, right? Then Sorensen Dice is pretty similar to Jacquard, but they don't, deduplicate tokens. They just use all the tokens. Jacquard actually deduplicates tokens. And TF-IDF plus cosine, which basically uses the TF-IDF vectors and then calculate the cosine product, the cosine similarity between them, and try to find a distance out of that index. As you may know, the cosine similarity is basically the dot product of both vectors divided by their magnitudes multiplied. And then we have the embeddings based, which are the most scalable ones and the ones that we really use, which are Euclidean, cosine, and word movers distance. Euclidean and cosine are very straightforward. Word movers distance, we won't be covering that one, but it's kind of the most accurate one in terms of document similarities. Okay, so now we have vectors and distances, and we have different ways of kind of building up the KNN. We can either do unstructured KNN, which is basically brute force. We end up comparing the sentence to the full knowledge base, right? And we can do that in terms of plain comparison or weighted comparison. That's the W in KNN, W in the W in KNN version. Or we can do some centered comparison by grouping some structures first, and then classifying into a set of entities, and then just comparing to this subset of entities. We actually use this kind of solution in our ensembles. And then we have the structured ways of doing this, which are basically building trees out of the vectorized versions of the sentences. We can either build trees, or we can either build some kind of self-organizing maps like the Cojones map, for example, and then being able to quickly first classify into a set of entities and then comparing just to a subset of entities. And generally, the structured one are the most used in order to be to work at scale. Okay, let's go directly to our solution. What are we using in our solution? Okay, first, a little bit of, as if I may say, housekeeping item, just to mention that our library follows an annotation framework in which an annotation is defined by these 5 or 6 attributes. They are type, the type of the annotation, either if it's a token annotation, or it's a chunk annotation, or it's a document annotation. As you may know, there are hierarchy, right? A hierarchy of the text. You have the document, then you have the sentence, which is actually another way of expressing a document. And then you have the chunk, which is a set of words smaller than a sentence. And then you have the token, which is basically a word. And then you have the most complex type of annotations, which are part of speech, named entity recognizer, and resolved entity, and so on. We also have a begin and end attributes, mainly the indexes of whatever content the annotation is referring to, then the actual result of the annotation, and then a metadata field. The metadata field basically gathers information that we have calculated doing the annotation, and we just present it to the user. And at the end, at least for the embeddings-based annotators, we have an embeddings attribute, which is a vector of floats, and basically saying what is the embeddings of the given text, starting in begin and finishing in end. Okay, so now that we have an annotation clear, let's see how we do our entity resolution. So what do we have for preprocessing stages? In our open source library, we have these kind of preprocessing techniques, mainly sentence detection, tokenization, stop word removal, and embeddings calculation. So most of the entity resolution pipelines will have these preprocessing as the first stage of our process. And we have convenient functions for all these preprocessing stages. Assembling the document first, of course, then detecting sentences, tokenizing, having embeddings. Oh, I missed the word movers, the stop word removal there, but we also have a line of code for that word removal. Okay, we have covered preprocessing, and we have APIs for all the preprocessing stages. Now we go ahead and index the data set that the knowledge base that we later want to resolve to, right? How do we do this? Basically calling a fit function, like usual, right? And what does this fit function do in our solution? Well, basically it will calculate centroids for every chunk, for every set of words constituting an entity, and then it will try to build a KD tree behind the scenes with all those centroids, right? And we'll store in the tree, will, besides storing the key, which are these embedding centroids, we'll store the normalized and the trained variation for every single concept. So you may have different variations for the same normalized concept in order, to cover like a vast amount of versions. And then after we have built this tree, of course, you're able to serialize these and store it to disk for later later predictions, right? So this basically covers the whole indexing process, and we use centroids and we use KD trees to build this index. Then we go ahead to the comparison stage. We also have an API, of course, for this comparison stage, and it's basically the transform function. In the transform function, which is part of the model that we have just serialized, right? We will go ahead and start finding k neighbors for a given input. So we will start searching in the KD tree in an n log n order of algorithm. We find k, let's say, candidates for this input. And then in these candidates, we calculate 6 different distances, at least so far. We actually keep increasing the number of distances implemented. As of today, we have 6 distances, mainly the word movers distance, which is based on earth movers, the TF-IDF, Cosine, Jacker, Saracen, Jargon, and Levestein. So what do we do with these 6 distances? Well, we can treat them like features and feed them through either more complex classification logic downstream, or we can use a weighted aggregation of these distances. So we support out of the box the weighted aggregation. We have either max, average, or mean aggregations. And then after aggregating the distances, we also provide a parameter, 2 parameters to kind of narrow it down the results provided to the, or actually returned as metadata, right? We give you an A parameter that basically you can select how many results you want to get. And we give you also a distance threshold parameters in order to also filter the results by a distance threshold. And we also give you a parameter to get all the metadata involved in the calculations, and you can use these metadata as features for downstream classification tasks. The classification, of course, I just mentioned that we do out of the box is basically selecting the top match in terms of the aggregated distance. Just to tell you a trick, generally the best working strategies to perform the aggregation is max pooling of the distances. So, okay, we have now covered 4 of the tasks with their respective APIs, right? Mainly the pre-processing stages, the fit for the indexing stages, and then the transform for the comparison and classification stages. At the end, we have our evaluation, in which we provide APIs to not only calculate precision, recall, and F1 with the top match, but also with the hits at K, mainly a ranking kind of evaluation, right? You grab the top K results and you see if the correct result was in that top K, those top K results that you selected to return the alternatives. So that's nice. That's great. We have covered all the 5 stages. Kind of how do we solve these using our API, right? Our models. And now we can actually go ahead and take a look at the demo. So we have multiple pre-trained models for this. In this case, we will use one embeddings model, 4 named entity recognizers, and 5 entity resolutions models. You can check the whole list in our models repo. We have many more that you can use and combine as you wish. In the demo, we will see basically a common preparation for both notebooks, the document assembling, the sentence detector, tokenizer, and embeddings. And we will then, in the first notebook, resolve towards ICD-10-CM entities and RxNorm entities. For those, we will use 2 named entity recognizers. In red, you will see the pre-trained models, basically an NER that we at JSL developed from our own annotations, and then at drugs, NER that we develop given some FDA and Met mentions data sets. Also, we have an NER in the second notebook. Sorry, we're going to use an NER for cancer type of entities, and an NER for generic clinical type of entities. The cancer ones, we will resolve them to using ICD-10-CM neoplasms subset of codes, and the ICD-0 for histology. And for the clinical terms, we will use SNOMED as the resolution knowledge base. So, okay, let's go ahead and take a very, very quick look on how these notebooks look like and how a developer could make use of our library to resolve. As usual, you got the imports and a little convenience function that we have that is called with a secret code in order to start our Spark session. And given this and a specific data set that we have as model, and that you can take a look at the nodes, the kind of nodes that we're classifying right now, at least the top 20 nodes, we will jump right into our pipeline, our resolution pipeline definition. So here we have our 2 resolvers, right? Basically ICD-10-CM resolver and RxNorm resolver. They're pre-trained, and you need access to our models repository with a set of keywords that we will send, for example, in case of you buying our license or trying it. And then we basically build our pipeline over here. And we first do an RxNorm resolution, and with the results, we will then proceed to do the ICD-10-CM resolution. So at first, you can of course see here the preparation steps. Actually, the indexing steps, we have already done that, and that's what we call them pre-trained, right? They're pre-indexed. And then you have the resolvers over here and the transform function, which is taking care of the comparison and the classification. Okay, so you solve the code. Let's see what you get in the metadata real quick. As you have seen in the slide, you get basically the top match, right? Which you get in the result. The result text, that in the result, of course, you will get the code. In the result text, as part of the metadata, you get the normalized version of that given code, and then a couple of indicators to see how good this result was in terms of the confidence and the distance. And of course, the coordinates of the given chunks that you have classified. Okay, let's go and jump right into our results. I have defined a real quick metadata analysis function that just kind of handles the metadata and presents it in a correct way. And we can see how did this do, at least, for example, for ICD-10 CM resolution. So for example, coronary artery disease generally is related to these type of codes: I-2510, I-739, I-2542, and in this case, we just selected the top 5 matches, right? So those are the ones you get here, and a confidence score for the top match. We actually get the confidence scores for the full set of matches, but I just selected the first one to present here. And it's very probable that this code is the one related to this. And look at this, please, because this is really important to take a look. These are our results that we get as part of the embeddings mechanism, because no keywords are actually in common, other than, oh, we have coronary artery, right? But let's take a look at a better example in terms of not having keywords in common at all. So look, we have, let's see, okay, CMV infection. These are the ones that you, what is CMV? The model knows what CMV is based on embeddings and knowing that another way of calling cytomegaloviral disease is CMV infection. So you see, you have no keywords in common, yet the model performs really well there, and so on, right? Let's go directly to the RxNorm resolution. And these are pretty much easier, right? Because they're a bunch of one token, single token expressions. Let's take a look if we have multi. Yeah, but these are exact matchings. So, but this is kind of the message. We will get approximate matches because of the usage of our own embeddings type of encoding the text. So we have multiple sets of embeddings in our enterprise version, mainly for clinical and healthcare domains that do really well in semantic awareness of the different concepts. And let's also take a look at this SNOMED demo real quick. We also have some cancer-based notes that we actually grasped from the internet. You can also take a look at the links, because these are public links that contain these notes. And let's just jump right away into the results. So let's see. It didn't do really well in the first one, but let's get a better confidence ones. So here you have left scrotal swelling, and you say swellilum scrotum. You don't even, they are not even spelled in the same way, but which it managed to get that as the top match. Or you can also have, let's keep going through the results. I don't know if these are big enough. I'll zoom in. Testicular germ cell. Look, germ cell of testis, testicular. Well, you may say they are similar, but they're not that similar, and so on. Cytokeratin. So we pretty have good results in the resolutions and considering these scores and considering the, so look, solitary leukocytosis, white count, it got white count abnormal. Okay, this is it. This is for SNOMED, which is a really big data set with hundreds of thousands of different codes, and we're kind of resolving and classifying correctly over that large domain. Let's jump right into the cancer results. For example, in the case of, look at this, testicular germ cell tumor, and you have like malignant neoplasm of unspecified testis, malignant neoplasm in general, malignant neoplasm right ovary. Okay, this was not that well, but it got the semantics that the testicles and the ovaries are around the same state, part of the different gender bodies, right? So that's also good. And then we have different, for example, oh, here's an example. But that was really simple. But for example, lymphocytic lymphoma, and you have lymphoblastic lymphoma. I'm not doctor here, but I think these two are synonyms or some kind referring to the first type of lymphoma. But then you have this other small cell B-cell lymphoma, which is also related with the lymphocytic lymphoma. And all these relationships are not based on tokens or keywords, they're based on embeddings. We have the other example for central nervous system, which in the ICD-10 is generally either specified as these two code, either 8589 or 8380. And right next to the cancer definition of the diagnosis, we also have a histology resolver for ICD-0, if you are familiar with it. In the case of testicular germ cell tumor, it found that it was probably either a mixed germ cell tumor, because probably it's more common to find this kind of histology in this kind of cancer, or either this one here. Or in the case of pelvic muscles, you have renal cell carcinoma. No common words at all, but probably masses in the pelvic have to do with some renal abnormality. And these are all the relations that you get through embeddings and the embeddings that we have. So this is pretty much for the demo. And I hope it was graphical enough as to express how this is not at all a keyword-based entity resolution. This is a lot more complex than that. And it's using the different kinds of embeddings that we have trained in our own enterprise version of the library. So I think this is pretty much what we have to cover today. And I really appreciate your time and just want to hand it to Julia if we have any questions.
Awesome, thank you. Yes, just a reminder to please type any questions that you guys have into the GoToWebinar control panel. And we do have a few that came through. Looks like the first one, what other ontologies do you have models for?
Okay, let's see some. Let's quickly, if to answer that question, please allow me to go to the to our models repository and take a look at what other ontologies do we have. Sorry, do we have there? So apparently the presentation is lagging a bit, but I can tell them from the top of my head. We have resolution models for RxNorm, SNOMED, ICD-10-CM, ICD-10-PCS. We have also for CPT, and we have another one for ICD-0. And the full list is right here. Oh, and not only that, in case you have the need for more specific analysis, we also have smaller versions of these ones based on different ranges for the code. So we have a diseases for ICD-10-CM resolver, an injuries resolver, a musculoskeletal resolver, the neoplasms resolver that we just used in the demo, and then a puerile resolver. These are a lot smaller than the full one here, or even the full one in the ensemble version, and they're going to be a lot easier to use and download and all this stuff. And here, when you hover over the data set icon, you will get what ranges the resolvers work for. In this case, the A000 to N999, and so on. The musculoskeletal is going to be from M00 to M99, and so on. So you get also what are the ranges that they cover from each ontology. The bigger ones are the ones based on the ensemble resolution, which are mainly RxNorm and SNOMED, and an ICD-10-CM that has a lot more variations, probably in the hundreds of variations per code. So we will make sure you get every single code correct, at least with this architecture of resolution.
Awesome. We had a few more just come through. Why are some of the RX matches have low confidence even though they had exact match? One example was Tylenol.
That's a great word. That's a great question. Sorry. That's a great question. In this case, it also depends on the parameter that you use for the, let's go ahead and open up the RxNorm. It also depends on the type of confidence calculation that you use. In this case, we use the softmax calculation. We also have this inverse square distance calculation. And let's go directly to Tylenol. I didn't see it specifically, but let's go right there. So as you see, it doesn't mean that it's bad always, right? It just means that compared to the other results, it's not that perfect. But for example, in this case that we have selected the 5 top matches, we will be getting at least 0.2, right? 1/5 of confidence for each match. So it's kind of over the 0.2. So it's probably we're probably confident enough that the first one is the correct match. But wait, there's also a probability that this is the correct match. And probably this was a children hospital note, and you would rather select this one than the other one, right? So it's just that we provide enough resolution items, and this is, for example, in a UI, you will be able to perform your own classification logic and quickly click the one that makes more sense, for example. But yeah, that's a very good question. It's not only a low score does not really mean that you have a bad result. It's just that you have 5 very good results, for example.
Awesome. One other one, can I extend on top of your comparison logic to add additional comparison logic specific to my business needs?
Yes, that's a great question. And yes, so with the use of one parameter that you can also take a look at of course, the library Scala docs, the documentation, but with the usage of this parameter called all distances metadata, you will get all the distances that we have calculated during the resolution process, and you can use these distances to perform your own logic. Either optimization for fine-tuning logic or either classification logic. So yes, we have all the information that's needed, and yes, we can help you with the algorithms to build that classification logic on top of it. Because at the end, these are just features. These are just features that can be used to another classifier.
Awesome. A few more came through. Hopefully we can get through most of these. Someone said, hi, I'm involved in trauma network advice. This looks like more of a research tool rather than diagnostic tool. Do you do anything with LOINC?
That's a good question. We have the lab tests results on our roadmap, and we we do think we will be able to train pre-trained models for this kind of ontology. LOINC, yes, the one for lab test results, if I'm correct, yeah.
And then someone asked, does the product help to determine entity relationships in a document apart from basic entity resolution?
At least the one that we're presenting today is not doing this, though we have different name entity recognizers that will help first in parsing those entities out of the preform text, and those entities will let us calculate, of course, different types of features that can be used for inferring this type of relationships. So short answer, sorry, would be not yet, but we're already in the workings to first merge all the NERs that we have into one single kind of feature extraction, and then feed in these to entity relation model.
Cool. Then we had a few more come through. Notice the high association score of testicular germ cell cancer with ovarian malignancy. Of course, every model has false positive outliers. Any explanation for this particular one?
Yes. To be honest, the actual high testicular, the number one was here too, malignant neoplasm of unspecified testes. Like this is the one. So it's probably, I mean, we can say that the malignant neoplasm of right ovary match was not high enough to either compete with the top match. So, there was not actually a high confidence score for this one. It just appears as the top 5 in the top 3 actually, but the one should also tell us that the only one to consider is going to be this one. Nevertheless, we have also in the metadata, we have results for confidences for all of the rest, but they're probably going to be 0 in this case. So, and again, this is just because we have indexed our data, the models in our data, in the data that we have prepared for this. We can rebuild this index on demand, so they fit and they can, adhere to the distributions of keywords that you actually have in real world applications.
And then there was
These are just pre-trained
another.
models.
There was another question. I noticed on one of the examples that you showed that with high confidence, it turned a testicular cancer into left testicular cancer, presumably by joining the word left in the next sentence. Is there some way to suppress that kind of behavior? The left was related to the foot, not the testicle.
Oh,
and then there's another part to that. I'm also curious as to why you aren't using apparent presence in coded values in the text.
I will answer those 2 questions with one. Well, let's say this kind of comparison that we're doing right now is really simple. It's based on as I mentioned, a centroid, right? And then 6 distances. But in the distances, we do not classify tokens into different type of sub-entities. So a way of handling the left thing there, right? Being, for example, a laterality related to something else, we would need a more complex entity resolver architecture that, as we speak, we're working on it, but let's stay on this particular architecture that we're presenting today. So the short answer is we don't have that in the specific resolver right now, but everything could be either addressed in the pre-processing stage or in the embedding stage, right? Actually, the same thing, the pre-processing stage. So some stop words can be removed from the entities, right? And then just feed the ones that are part of that are not part of stop word vocabulary, or a whitelist type of vocabulary, just fit the ones that are there. So there are different ways of handling this. The model itself on its own does not really handle this yet. We're working on an architecture to take into account subtypes of entities and perform attribute-based resolution.
Great. We did have a few more questions come through, but I know we've already gone a bit over time. So we can follow up with those of you who have asked questions individually, or we'll send out answers to all of those questions in one combined document. I did want to let everyone know that we will be having an upcoming Spark NLP virtual training for healthcare data scientists on May 13th from 12 to 4 Eastern. So we'll be sending over some more information on that. You will also be receiving the recording for today's webinar within the next couple of days, so keep an eye out for that. And there are 2 other webinars already on the calendar that are open for registration. So we'll send over the links for that as well. And with that, I will thank everyone for your time, and we will see you on the next one. Bye, everyone.
Thank you, guys. Goodbye.